All right, we're going live now. Hi everyone, how you all doing? Welcome to our first webinar of 2025. My name is Ali Parandeh. I can't wait to join you on this webinar today, where we're going to be talking about neural networks and how they work. So we're going to basically start from the fundamentals and build the concepts all the way towards a practical demoable application, working with an actual data set. My name is Ali Parandeh. I'm just hidden myself for now, but I will show you myself here now for you. Basically, what we're going to be doing today is discussing how these neural networks work from the ground up, so you understand, like how these neural networks work from scratch. And essentially, what we're planning to do with this webinar series and workshop series is to basically cover different topics in deep learning and machine learning through some of these workshops and webinars. So I know the beginners machine learning group is basically a group where we dedicate to learning these concepts and tools together, and these workshops through this series of these workshops. And this is essentially one of our webinars starting in 2025, where we're gonna go and cover some of these concepts in relation to machine learning, AI, and neural networks. So basically, to give you a bit of a background about what beginners machine learning is, essentially we are a meetup group based in London. We've been around since 2018. We've been running several workshops, as you've seen from Meetup. I think this is our 30th workshop or webinar. We're going to be starting with a couple of webinars, but gradually we're going to be moving this into in-person events. We used to do this events at Microsoft Reactor, based in London before pandemic. But now, starting from 2025, we're going to start going into more running some of these events where we're going to discuss various different topics from deep learning, reinforcement learning, natural language processing. So all of the workshops we will be doing is going to be free, and it's all going to be educational. And we may also have several talks from various different experts in this field to help you with getting started and break into this field if you haven't already. And if you're already working in the field of AI and data science, getting practice with different tools and techniques and getting some hands-on experience with going into some of these topics. So if you haven't already, go join the meetup on Beginners Machine Learning London on our meetup group, so you can get involved and hear more about any of our future events. And this is basically our first event in 2025, where we're going to be covering various different DL, deep learning, machine learning topics. And we're going to start from the scratch, from the ground up. So if you haven't seen or haven't heard details of these neural networks and deep learning and machine learning, and you're feeling, perhaps lost where to begin, this is exactly the kind of workshops that we want to, deliver to give you an idea of where to go from here onwards. So essentially what we've planned for 2025 is a series of workshops. This is just a rough idea of the kind of workshops you will be seeing in the coming months and in the coming weeks. The first one, which is this workshop, is going to be covering neural network fundamentals. But the workshop series that we have planned for 2025, we're going to be covering computer vision. We're going to cover natural language processing with Hugging Face transformers. This specific workshop for today, we're going to be covering deep learning and neural networks, but we're not going to go into convolutional neural networks and more advanced topics. Other topics we're going to cover in future workshops will be reinforcement learning, generative AI. We're going to then switch gears into classical machine learning, focusing on what machine learning is and the fundamentals of it. Regression, classification, clustering, time series forecasting. So all of these are different types of workshops we have planned for you. And it's very exciting because all of these will be hands-on. We will be providing you with resources so you can actually get hands-on practice as we go through the webinar. Same thing with today's workshop. We're going to be giving you a couple of links on Google Colab, so you get a couple of Jupyter notebooks you can play with, so you get some experience with working with some of these tools. After covering some deep learning and machine learning, we're going to then be focusing on cloud computing. So working on the cloud, working with tools like Microsoft Azure and AWS, and covering a data engineering concept a little bit, so you don't just necessarily just work from the notebooks. We're going to be assuming some programming experience in Python, but if you haven't, you still can follow through, because we're going to go over every line of code and we're going to explain how things work. And you don't require you to install anything on your local computer, because everything will going to be run from your browser, so you don't have to fiddle around with setting things up on your local machine and trying to get some of this code working. So essentially, these will be some webinar series and some in-person series. In April, we are currently working on setting a date where we're going to be actually doing a generative AI workshop in Microsoft Azure, which we're going to be focusing on, and all of this will be free, focusing on how to build and deploy generative AI services on Microsoft Azure with Azure AI Foundry. So I think we have a preliminary date set up with Microsoft Reactor based in Paddington. So save this date on 1st of April. We're going to be publishing the event later today or tomorrow on our Meetup channel on meetup.com. So you can join this event. So it's about like 35 spaces for this hands-on classroom style workshop. So this is going to be an in-person event where we're going to be running a workshop. You can see in the background there's a picture of one of the workshops we've run in the past. So I'll be hosting this for you on generative AI services, and we're going to be over the year bringing in more other type of experts to do some of these workshops for us, and webinars and talks. So it doesn't necessarily need to be just me. So with that said, let's get started. You might be wondering who I am, like what's this everything going on. So I'll tell you a bit more about myself. So my name is Ali Parandeh. I come from a mechanical engineering background, so I was a mechanical engineering consultant working for a multinational consultancy based in London. I switched careers later on to work into AI after I got my chartership with the Engineering Council. That includes getting certifications with Microsoft, becoming a data science consultant, and a developer as well. I have worked in rail tech startups building computer vision tools, as well as NLP tools, natural language text processing. And later on, I joined a data science consultancy based in London, Applied Data Science Partners, as a head of engineering to build AI-powered applications. And recently, I just managed to finish writing the manuscript for a book on building generative AI services with Fast API, which is a Python web framework. So if you want to productionize any kind of generative AI models, either from Hugging Face or any other model repository, you can take this book. It's available right now on Amazon for pre-order, to be able to get on and started with these services. And that's basically what we're going to be covering in that workshop as well on in 1st of April. So all of this will be free in that workshop, as well as any kind of webinars that we're going to do from beginners machine learning. So that's what this whole meetup is dedicated about. So with all that said, let's get into the content of today's workshop, which we're going to be covering about where neural networks sit, and in relation to AI, in relation to machine learning, deep learning. These might have been some of the concepts that you might have heard in the past, and you may be wondering what is this whole thing is about, and how you can get started building your own neural networks from scratch, and what are the tools and techniques available for you to do so. So if you go all the way back up to the beginning, AI has been around since the invention of computers. Basically, a lot of computer science researchers have been trying to work around themselves, figuring out AI and what it is. However, it's only been in the past few years, in the past 10 years, where the computer hardware has reached a point where we can actually use the algorithms and the mathematics and the statistical models to be able to run these mathematical models on the computer hardware. So AI has been around for a while. And the whole field and the field of the computer science around this was around mimicking human behavior through the use of computers and through use of scripts. However, it's only been recently where it's been possible to really build machine learning and deep learning and AI models that have been capable of surpassing human capabilities, basically. A subset of AI where most businesses would be interested in is machine learning, which is focusing on building models that are based on statistics. So these are statistical models that uses computational mathematics to learn patterns in the data so that it can then make predictions on new data points that they would see in the future. So they are basically prediction machines that you can use to automate the decision-making processes, to automate categorization of documents and data sets, to make predictions on values. So machine learning has been basically a subset of AI that has been used quite a lot recently for any kind of business application in these various different markets. So what machine learning does is that it's like a white box. You can actually use different techniques to create these models, and we were going to cover them in a later workshop. What we're going to be focusing on today is on deep learning, which is a subset of machine learning, so a subset of statistical models in the AI field that is focused on neural networks. So they use neural networks as the fundamental technique in order to map any data set from input to the output. So in order to be able to build models on any kind of data. So these neural networks, you run your data through them, and these neural networks learn the patterns in your data, and then you can use that to make future predictions based on any new inputs that come to these neural networks. So essentially, if we break this a bit further, the kind of problems that you can solve with both machine learning and deep learning is in terms of reinforcement learning, supervised learning, and unsupervised learning. So these are like different types of problems that these techniques can solve for you. And essentially what they allow you to do is they allow you to forecast numbers, predict categories, predict numbers from your data set, and perhaps with unsupervised learning, you can cluster your different rows in your data together to find patterns and relationships. If you're applying it in marketing, you can segment your customers with it. So there's a lot of different applications with neural networks. And what we're going to be focusing mostly today is on how to build them on a couple of cases and use cases, so you can kind of fully understand how you can apply it on your own data set afterwards. So we're going to be focusing on deep learning, but in a future workshop, we're going to go around into machine learning and talking about what reinforcement learning is, what unsupervised learning is, and what supervised learning is. So I know I would assume that most people would know these, but they would be interested in what deep learning is and what neural networks are and how they work. And that's exactly what we're going to be covering in today's workshop. So I'm going to hide myself so you can see the full content of the website, the slides. Essentially, what neural networks are a series of neurons connected together. And in order to fully understand the algorithms under the hood, let's focus on essentially what a biological neuron works, and then build our way from there. So neural networks, essentially under the hood, they have been based on a biological neuron. So computer scientists looked at how biological neurons work, and then they tried to figure out if humans and animals and humans can learn skills, and they have neurons in their brains, and how is it that these neurons work together in order to be able to learn a skill? Like, can we actually use that and to make artificial intelligence to some extent? Essentially, if you just zoom in at one neuron, you don't need to know exactly the different components of it, but how they interact together, that makes it interesting. So any neuron is connected to other neurons, and these neurons are sending any neuron the signal, either positive or negative, right? So the signal is either exciting the current neuron or is inhibiting the current neuron. So we call it excitatory signals and inhibitory signals. If there is enough of the excitatory signals, there is essentially a polarization happening inside the neuron. And after a certain threshold, it triggers an action potential, or it triggers the neuron to fire to the next neuron. So any neuron inside the neural network, inside your brain, is connected to other neurons, is receiving signals. And if it receives enough signals, it gets activated and sends a signal to the next neuron. that is connected to. So, and if it gets inhibited, it doesn't send a signal. So it kind of stops the pathway of the neuron as in the neural network. By itself, this is essentially what the neuron does. It receives a bunch of signals from various, so it has a bunch of inputs and it has a single output, right, or a bunch of outputs, depending on what what other neurons is connected to. And if the inputs pass a certain threshold, it gets triggered and it gets activated and it sends a signal and it fires that signal to the next neurons that it has been connected to. So computer scientists essentially decided to look at this specific neuron and try to create a simplified mathematical model from it. So they looked at the biological neuron, and then they said, okay, let's create an artificial neuron from it using mathematics. So we can build a statistical model on top. So whenever we talk about a deep learning model, it's essentially a model that consists of a bunch of neurons connected together, creating a neural network, and each neuron has a certain essentially mathematics going in it in order to make it work inside a neural network. So especially with this one, the mathematics is essentially a very simplified model that allows you to map this any kind of input to any kind of output, so you can create a model, a statistical model from it. So in order to understand this a bit further, what I'm going to do is I'm going to just show you some of the mathematics around it in a model that I have here. So essentially, in terms of what's going on and what's happening with under the hood with these neurons, is you have a certain nodes, so certain neurons that are connected together. They receive a bunch of inputs, and these inputs go to the neuron to the next one, right? So basically, if we call this neuron 1, neuron 2, and neuron 3, what's happening is these neurons are receiving some input. So if you just look at and focus on the neuron that I have highlighted here on this one, it's receiving some inputs from neuron 1 and neuron 2, and it's sending an output going out on the right hand side, right? Now if you go back to this example here, you can see that the inputs have some kind of weighting on them. So you see the x1 input has a weighting of W1, x2 input has a weighting of W2. They get summed together, and there is some kind of activation function that allows it to go out. So essentially what's happening here is you have x1 and x2 coming in, that's your data. They get multiplied by W1 and W2, so you will have x1 W1 plus x2 W2, and this essentially is at a simplified form what's happening under the hood with each specific neuron and how the output of that neuron is calculated. Now the main problem with this specific function is that it's a linear function, and there is so much you can do with linear models. Like you can't actually map any kind of complex inputs to any complex outputs, right? So normally you don't necessarily just sum the multiplication of the inputs with the weights or with the W's. What you need to do is you need to pass this whole sum through something called an activation function to introduce some kind of nonlinearity, right? So normally you will see in the calculation for the output of any specific neuron, there is some kind of activation function that applies some element of nonlinearity to the output of the model, right, to the output of the neuron. So if this neuron says like 33 comes out from the end, the activation function might squish this between 0 and 1, or the activation function might squish this between -1 and 1. Perhaps maybe if it squishes it between -1 and 1, you might get let's say 0.4, or with this one you might get 0.1, 0.12, depending on the results of that activation function, right? So depending on what activation function you use, you might get some kind of squishing going on, or some kind of like truncation of the output in order to first help the neural network learn the data and the patterns better, And then the second would be the fact that these neural networks allows it to converge better on the data. So it's basically it adds some element of nonlinearity to the mapping of the input to the output, right? So by itself, these neural networks, essentially that's all it's doing under the hood. So they're just adding the multiplication of each input with the weights and then squishing the output between some set of numbers and some values, right? So if you look at some of these activation functions for each specific neuron, you will see we have all of these different types of activation functions here. I will just copy them into our Figma board so you can easily see the different types of activation functions we have. So the output that comes out from the neuron, each one of the specific neurons, they then go through one of these activation functions. So either they get maxed between 0 and that number. So if the number coming out becomes minus, it will get truncated towards 0. You also have other types of activation functions, and each one has a specific use case. And most of the time, for depending on where the neuron is in the neural network, you might see a lot of ReLU activation functions being used or leaky ReLU activation functions being used, depending on the different where the neuron is and what the use case is that you're trying to build a neural network for. Different activation functions might get used, but these activation functions do is they try to introduce an element of nonlinearity in this function, which is linear by definition, as you can see. And they also try to make the training of the neural network for each specific neuron much easier by squishing the numbers to a number between 0 and 1, for instance, instead of working with the number 33. Because if all of these big numbers start getting multiplied together, your computer will run out of space and memory doing those computations. So that's what the purpose of these activation functions is on a specific at a neuron level. There is also another element that is added in at the end between these, and we call this a bias. So for each specific neuron, there is also an element of bias added in that allows the training algorithm to find to have more degrees of freedom in order to train the neural network on your data set. So it allows the neural network to also have more it will have more space or more capability to map any kind of inputs to any kind of outputs. So by themselves, these neural networks doesn't necessarily provide any kind of capability. Like it is just a simple function that maps some inputs to some outputs. By themselves, they're very simple. They are creating a very simple nonlinear function that maps some bunch of X inputs to a Y output. What becomes important is when you start connecting them together, you will end up with, when you start connecting them together like this in a neural network, you will end up with a more complex system that can map any input to any outputs. So as soon as you start connecting a bunch of these neurons together and you run that calculation that I showed you on any of the neurons, you will be able to build more complex models that can make very, very interesting predictions on your data set, no matter how complex your data set is. Most of the time, you will not want to use a neural network because these are really kind of like black boxes. Trying to figure out the mathematics that goes on under the hood with these neural networks are actually quite complicated. So normally what happens is with these neural networks is you will want to use them on data sets that are quite complex because the number of layers that you can add in these neural networks, the number of nodes that each layer could be quite difficult to know which one was right. And it's also quite difficult to open up and see what's going on under the hood. But as soon as you add the neurons together in different layers and you all connect them together, that's when the emergent properties of these neural networks become really important, and they become really capable of connecting any kind of inputs to any kind of outputs. A good way that I like to visualize these neural networks is you can visualize how these neural networks work essentially like a box that has a bunch of inputs coming in. So these are like your x1, x2, x3. So think of these as different inputs from your data set. So if you have, for instance, different columns in your data set, x1, x2, and x3 could be those columns. Each x1 could be column 1, x2 could be column 2. And then you're trying to build a model on some y, one of the other columns. And those W's become the knobs and dials on this data set, right? So think of this as a mapping function. So this fx is a mapping function that is trying to map the inputs to the outputs, and then you just basically adjust the knobs and dials of this massive case that has full of knobs and dials on it by rotating these knobs and dials towards right or left until you can map the y to the x's on the left hand side. So a neural network is essentially like a black box that has a bunch of knobs and dials on it, like a key, like a safe. And to when you have a trained neural network, is like you have cracked the safe. It's all about trying to figure out what are the best positions of these knobs and dials in order to be able to map these x's to the y on the left or on the right hand side, which is the whatever property that you're trying to make a prediction on, right? So each one of these knobs and dials could be W1, W2, W3, which are the connections between your nodes in your neural network. So a big neural network like this one, like a deep neural network that has many layers, will have a lot of W's. So it will have a lot of knobs and dials that you will need to adjust. And that's not something you do. That's something the training algorithm will do in order to figure out how to go from the input layer to the output layer and adjust the neural network in such a way for it to work that way, right? So when you start a neural network, essentially when you connect these nodes together, let's say you have some vibration data set that you're trying to pass to the input to the neural network. When you have a untrained neural network, essentially it will be just a bunch of nodes connected together, and the connections on these nodes or the weights, they are all will be set to some random value near 0, and essentially the data gets it gets squished through the network in some random manner, right? When you have an untrained neural network. And then at the end, you might specify an output layer where each node specifies whether your component, if it has some vibration data, whether that component is broken or not broken. And the number that comes out from those nodes will specify the confidence. So 0.5 here means it has 50% confidence that it's broken and 50% confidence that it's not broken. And so some kind of probability that the neural network will calculate on the right-hand side. So when you train this neural network, what ends up happening is the weights get adjusted. So you remember these knobs and dials that we have in here. So then the training algorithm will adjust these knobs and dials in a way for the vibration data on the left-hand side gets mapped to the broken, not broken state on the right-hand side. So what ends up happening is that node that has the label of not broken will fire more and will have the number on it 0.97 that will say 97% confident. This neural network is 97% confident that this component, based on its vibration data, is not actually broken. It's healthy. And what ends up happening is, because those weights have been adjusted by the training algorithm when during the training process, you will see that some of these weights on the neural network is actually stronger. They will have a much higher number compared to the other weights that had been initialized at a random value near 0. And you will also see that some of those connections have a very number that is very, very, very close towards 0. So those connections will literally die down towards 0. So do you remember when I said they will have some inhibitory signals coming into some neural networks and prevents that neuron from firing to the next one? So some of those neurons will not fire anymore. So based on the patterns that this neural network has learned on your data set, which in this case is a vibration data, certain pathways will die down and certain pathways will get amplified. So there would be a certain neural pathways that become very, very important for mapping any data set from the input towards the output that you want. And depending on what output you want, you can use the same data set and you can create different neural networks. So one neural network could predict whether something is broken or not broken. Another neural network can train to learn to predict when something will be broken in terms of hours, days, years. So you can predict in terms of years, how many years before this component becomes broken and you need to replace it. You can train another neural network to predict in advance, for instance, how good or bad state something is in terms of some metric like health rates. So you can essentially train a neural network to give you any type of prediction, and all the neural network has to do, the training algorithm has to do, is try to figure out the connections, the weighting on them, in order to map that input to whatever output that you're trying to make a prediction on. And all it does is it figures out what numbers to put on the connections. So we call those connections weights, and each node will also have certain biases that it will try to figure out as well. It's just not visualized in this case, but when you have those connections, you will be able to do that. So this is essentially under the hood what's happening when you train a neural network. You can map any input to any output, and each node will have a really simple calculation going on it. Sum the inputs multiplied by their weights, then pass them through an activation function, and pass that to the next node. Repeat the process until you get to the end of the neural network. But this crunching of these numbers somehow manages to get you from the input to the output. And once it's trained, that output will have a meaning. It will actually be what you're trying to look for, what you're trying to predict on. And you can literally design your neural network however you like. So this is what we call a hyperparameter. So how many layers do you want to have in between? So you could have you will always have an input layer based on your data. So depending how many columns you have in your data or what you're trying to pass in, you will always have some output layer, and that output layer will be based on whatever you're trying to make a prediction on, whether it's categories or whether it's some value like a forecast. And the hidden layers, the layers in between these two layers, there can be as many of these hidden layers as you like, and there can be as many nodes as you like in these layers. So that's what makes it hard and difficult to build these neural networks. Like it becomes part art and part science to build these neural networks together, right? But there is an intuition, and if you know that intuition, it allows you to design these neural networks better. One part of developing that intuition is playing with some tools that I will show you now. Another part is by looking at research papers and by having an understanding of what's happening under the hood in terms of the mathematical side of it. So understanding the intuition of how these neural networks work. For instance, normally, as you go from the left-hand side of the neural network towards the right-hand side, what ends up happening is neural networks learn the basic patterns in your data on the first few layers. And then in the next few layers, they will learn more intermediate level patterns and then more complex patterns. And those later patterns, the more complex ones, are built based on the more intermediate and basic patterns. So to give you an example, let's say we're building an image classifier that is classifying images of people. When you pass that image through the neural network, it will learn edges. It will learn like vertical edges, horizontal edges, so patterns like edges in the first few layers. In the next few layers, like halfway through the network, it will start to learn shapes, like what does a rectangle look like? What does a circle look like? What is a rectangle? What does a triangle look like? So it will start to detect what shapes look like and what they mean. Then it will then combine those shapes in the further layers in order to create features. Like for instance, what does an ear look like? What does a nose look like? What does an eye look like? By just putting those shapes together. And then at the last layer, it can make a prediction based on those complex patterns that it has learned, based on those features. So we call it features, based on complex patterns that it has learned at the last layer to make a prediction. Right? So if you try to visualize this, you will not be able to see those patterns yourself. But under the hood, in terms of the abstract concepts, that's what the neural network learns. So your data could be any kind of data set. It could be a table, it could be images, it could be video, it could be text. What ends up happening is under the hood, you have this black box that as you go from the left-hand side of it towards the right-hand side, towards the output, it learns basic patterns. Then from those basic patterns, it learns more intermediate and complex patterns. And then at the end, the last layer will run based on those complex patterns that it has learned in the layers before. Right? So a good way to get this intuition, to understand how these neural networks work, is there is a really nice tool called the TensorFlow Playground, where it allows you to experiment with different data sets, and each data set has like different patterns in it. And what you need to do is you need to be able to design your neural network in a way that allows you to map the input features towards the output features. Right, so I'll just give you an example of what this playground looks like. So if you just go to playground.tensorflow.org, you would be able to see, you would be able to play around with this. I'll just post this as well for you in the live chat, so you can go around and play with it. Essentially, this allows you to run a neural network in your browser, and you can see the number of epochs, which stands for the number of iterations over the data set. So number of times the data set has gone through the neural network and the neural network has been trained on it. And you can see once the neural network is trained, the connections that are important to create this model, those connections will have a much bigger weighting adjustments on them. Right, so you can see the weight on this one is minus 2.4, the weight on this one is minus 2.1. But if I reset the network, all the weights will be some random value near 0. Right, but once I get it trained, you will see that the connections that are interesting and are important for mapping the input towards the output, in order to get this model that you will see on the right hand side, those connections get adjusted bigger. And you can see by adjusting the weights on this how I'm changing the model on the background. So the background color shows the boundaries, decision boundaries of the model. And what the model should try to predict is it should try to predict the best decision boundary in a way that all the data sets, all the data points are categorized correctly. So this isn't a classification problem, but you can also do the same with regression. I try with classification. So you can start with a simple example like this one. So this is a really easy one because a linear model can easily map it to the input output. But as soon as you go towards more complex examples like this one, you will see that just running the same network on the data set doesn't produce a really good results. It has actually a hard time trying to create a decision boundary around your data points in a way that maps the input towards the outputs, right? And you can see on the right hand side the various different metrics you have access to in order to check if this model is training or not. So have a go and play around with this tool and try to understand the intuition behind what you need to do in order to make sure that you can map the inputs towards the outputs with this specific model. Essentially, what you're trying to achieve here is you're trying to find what architecture you need to use and what you need to do in order to map the input towards the output with this neural network, right? The main idea behind here is because this is a complex data set, you probably need more nodes and layers inside this neural network. And also because there is a very complex data set in here, you probably need more features or more signals coming in from the left hand side. So you will probably need more columns in your data set that have patterns in it. You need more patterns in order to be able to map the input towards the output. And perhaps you need to set this to train for a bit longer in order to be able to in order to be able to build a model that is actually mapping the input towards the output correctly. Right, so you may experiment with the features that you pass in. You may experiment with the number of nodes and hidden layers that you pass in, and you may experiment with some of these other settings that you see at the top here, like the learning rate, how fast it learns, what activation function to use, etc. So these areas specifically, right? And you can see in here, in terms of being able to compare your results between different runs, we have a metric called a loss, which is an error rate. And you can essentially use this metric to compare your different experiments together. So the lower you can get this towards 0, the better your model is. So you have a loss for your training and you have a loss for testing. Think of this as homework questions. Think of this as your exam questions. So as you're training, you're going to be evaluating your model against the training data. But once the training is done, you're evaluating on a test data. And this tool is doing that at the same time. It's doing it as it's being trained. Right. So it's a really nice tool to get the intuition behind how these models are actually working. Right. So essentially, what's going on under the hood is that in order to calculate the error rate, we have something called the loss function. And all the loss function is doing is comparing the output that is coming from the neural network against the actual. So it's for instance, if you're building a regression model to predict some value, it's calculating what the error rate is. So if you're building a model to predict prices of cars, if your model is predicting 10,000 pounds and the actual car price is 12,000, you have an error rate of 2,000 pounds, right? So if you do that across entire records in your data set, what the loss function is trying to do is trying to figure out how the different weights and biases are influencing this error rate. That's what this loss function is. So in this case, for instance, if you just look at two of those weights, so instead of looking at all of the weights, so instead of looking at all of these knobs and dials, if you just look at two of them, so if you just, let's say, look at W1 and W2, and we do a loss function on it, you will find that this loss function looks like some kind of landscape, and a process where you have to reduce the loss function is to figure out the direction of movement in order to reduce down. So the direction of movement, where do you need to adjust the knobs towards the right or towards the left? Do you need to go higher or lower in order to reduce this loss function in relation to those weights? So if you just visualize the loss function against two parameters, you will see that you will have a landscape, and the training algorithm perhaps uses a process called gradient descent in order to go down these landscapes, go down towards the lower end of the landscape, right? And what you see here in this landscape is just two of the parameters. Your landscape is your this landscape that you see is only two-dimensional, but you could have n number of dimensions, and the more connections you have in your neural network, the more connections you have, including the biases. So this is not a two-dimensional problem. The loss function is an n-dimensional problem. It's n dimensions. So it could be as many dimensions as there is number of parameters in your neural network. So, and in order to calculate the contribution of each of these knobs and dials towards the error rate, you need to instead of going forward, you need to work your way backwards in the neural network, right? So instead of going forward in this neural network, you calculate the loss at the end, and you need to make your way backward in the neural network and calculate the contribution of each of these connections to the error rate. And we call that backpropagation, this process. And it has to use some, different partial differential equations and the chain rule in order to make those calculations. So when you do a forward pass, you calculate the prediction, you compare that with an actual, you calculate the loss, and then you'll work your way backward to figure out what are the contributions of each of the weights to this loss value, right? And then you try to figure out, okay, if the contribution of this specific parameter is this much, do I need to reduce the parameter or increase the parameter? And that's what that's what the backpropagation process tries to figure out, is how much do I need to adjust each of the knobs and dials in this neural network in order to make the input get mapped to the output correctly, so the predictions become correct. So once you reduce down the loss function towards 0, that's when you have a trained model. So you use the loss parameter to make those predictions to be able to perform these calculations. And all of this sounds conceptual at the moment, so we're going to actually do demos in a minute to give you an idea of how you can how all of these work under the hood. So you can actually look at the code, and I will go through every line of code with you in a moment. One last concept that you need to consider is concept of model fitting, which is essentially when you train a neural network, if you're doing a regression problem or a classification problem, you don't want your neural network to learn the exam questions and memorize them. You want the neural network to learn from the homework questions and perform well on the exam questions that it hasn't seen, right? You don't want a model to memorize the homework questions and then go sit on exam by memorizing the homework questions. That's what an overfitting model is. So you want to train your model to an extent where it doesn't learn the noise and the outliers in the data set. It just learns the patterns, so that you can use it going forward with new entries and with new data set that it hasn't seen before. Right, so whenever you're trying to build some kind of regression model or classification models to make predictions on categories or numbers, if your model maps the inputs not enough, if it doesn't map the inputs enough at a good rate, you call that underfitting. So you haven't trained it enough yet, or the inputs that you are giving the model isn't good enough. It doesn't have the patterns that the model needs to map the input to the output. If you see that you're getting the charts on the right hand side, so you're getting a decision boundary that's really like all over the place, and you look at the results of the training loss and the test loss, and you see that the training loss is going towards 0, but the test loss is going higher as you're training the model further, you will see that you will have something called an overfitting phenomenon, which is your model is learning the noise and the outliers as well in the data set, in the training data set, and then it's trying to use that on the test data set. So it's memorizing the homework questions and then sitting down at the exam, and then it's trying to use whatever is memorized from the homework questions to answer the exam questions, which is you don't want. You want the model to learn from the homework questions, learn the patterns and the general concepts from it, go sit on an exam and be able to answer the exam questions that it hasn't seen before in a way that is correct, right? So like it learns the concepts and the patterns, not necessarily specific instances and examples. That's what you want to happen with this specific one, right? So looking at the practice of it, there are a couple of deep learning frameworks that you can use. So in terms of tools, the most popular one is Keras TensorFlow and Pytorch. TensorFlow Keras was they were a bit more popular in a few years back, but recently Pytorch has taken the show. So if you're gonna get started learning deep learning with one of these frameworks, I would recommend taking up Pytorch, although TensorFlow and Keras are also good contenders if you want to learn them, right? All of these frameworks, they are built on essentially they have been written mostly with C++ and programming languages that are closed down towards the hardware, towards the metal. So they're very fast, and they also, what they try to do is they try to optimize on a graphical processing unit to be able to parallelize the computations essentially, right? And they work on a data structure called a tensor, which is essentially a way for you to package up numbers. So you can use linear algebra to perform these computations that we see. So we will be having to do a lot of multiplications, and instead of doing them at a scalar level, which is by multiplying a bunch of numbers, what you can do is you can bundle up the numbers by putting them into a vector, then bundling the vectors together into a matrix, and then bundling the matrix together into higher dimensional boxes in order to be able to parallelize the computation on a hardware such as GPU that is actually optimized for like performing parallelized linear algebra calculations, right? So there is a concept called the tensor ranking. So tensors are essentially a data structure that can move between the CPU and the GPU, and all of these deep learning frameworks use that. And tensor ranking essentially is a concept where you package up numbers. So you can have a list of numbers called a 1D tensor, an array of numbers called a 2D tensor, a box of numbers called a 3D tensor, and if you go higher in ranking or in dimensions, you have a list of boxes, 4D tensor, an array of boxes, 5D tensor, and a box of boxes, 6D tensor. And then you can go even higher dimensions. What this allows these deep learning frameworks to do is that it allows them to multiply these boxes of boxes together in a parallelized manner to perform all of those calculations that we need to do for every neuron in the neural network. So that's why running these training processes and algorithms on a GPU is actually way more efficient, because you can parallelize them compared to running them on a CPU. On a CPU, you're literally doing it at scalar level to some extent, but CPUs are very fast at doing it, but you're still doing it at a scalar level, whereas on a GPU, you're doing it in a parallelized, vectorized manner, which makes them super efficient, right? So essentially, if you want to be doing any kind of model building in a language such as Python, the good news is with these deep learning frameworks, like for instance in Keras, you can build a whole neural network and train it in only 15 lines of code. So in this whole code, you can load the data, split it, define the model architecture, and you can essentially create a neural network in just a couple of lines of code and build it and train it and then evaluate it and test it and use it to predict stuff, right? So this is TensorFlow, for instance. It's a deep learning framework by Google. You can see in this code that the first line is loading the data and splitting it into a training set and a testing set. So X train is the training inputs, Y train is the training labels, X test is the testing inputs, and Y test is the testing labels. And essentially, you then test it, you normalize the data set and you split it. Then you create your model architecture using that sequential API that Keras provides. So you can see there is a flattened input shape 28 by 28 image that is going in, a 128 node layer, then a dropout layer, and then a 10 node output layer with a softmax activation. And then you just basically compile the model with an optimizer, a loss metric, and evaluation metrics that you want to evaluate the model on. That's all you give this deep learning framework. An ADAM optimizer, a loss metric, which is for categorical columns, because this is going to be doing doing a categorical metric, and then a metric for evaluation, which is in this case is accuracy. And then you just do .fit on the model, which trains the data set, trains the model on the data set, on the X train, on the training inputs, and the Y train, which is the labels, for 5 iterations or 5 epochs. And then you do model evaluate on X test, Y test. So testing inputs and testing labels. So in just a couple of lines of code, you have a trained model that it allows you to build from scratch, right? So because this is such a simple code that trains neural networks, TensorFlow became really popular. But recently, Pytorch is taking the reign, because it allows you to customize the training process as well. So you can actually implement how you train these neural networks at a more granular level, and also it's a bit more Pythonic. So you can actually debug it and look under the hood, whereas it was a bit more difficult in the past with TensorFlow and Keras, which may not be the case anymore. So for the demo exercise, what I'm going to be sharing with you and what we can do together, I will share you links to a Google Colab notebook that you can follow along with this webinar. Essentially, we're going to use a data set called the 3D printer data set. You can download this data set from Kaggle. So it's an open source data set. And essentially what this data set is you have a 3D printer at home, and you have 2 different materials, PLA and ABS, and you have different patterns that you can use to print. And essentially you print different components. So you print different components with the same design, and you measure things like fan speed, the material you use, the speed of the print, the temperature of the bed that you're printing from, the temperature of the nozzle that's injecting the material, the pattern that you have used. And then at the end, you measure 3 things. You measure the surface roughness of the print, you measure the tension strength, and you measure the elongation. So these are like different mechanical properties of the components that you print and measure, right? So what ends up happening in this case is essentially, you have these data set, and you can actually build a model to predict, for instance, the surface roughness, so that you don't have to you can essentially predict a model to predict the surface roughness for you based on the observations, so you don't have to keep printing stuff if you want to play around with the other parameters. So let's say you come up with an idea that you want to play around with the print speed and the bed temperature to see what type of surface roughness you would get. In order to one way is to keep printing different items and playing around with the other parameters. Another way is to build a neural network to make those predictions for you, so you don't have to keep printing. If you want to improve the surface roughness, you can use a neural network to play around and figure out what the surface roughness would be, or to predict the surface roughness based on some input parameters when you do the print, right? Essentially, what the neural network will learn is something called the correlation heat map, which is how each column in the dataset is correlated with another column. So under the hood, the kind of patterns that the neural network will learn is whether the surface roughness is positively correlated with other features or negatively correlated. So on the left-hand side, you have your columns, and on the bottom, you have, again, the same columns. And if you just look at the surface roughness, the column number 3 from the bottom, you can see how that surface roughness column is correlated with the other columns in the data set. And under the hood, what's kind of happening is that the neural network is learning this data set, these patterns in the data set, specifically with these neural networks, right? So what we're going to do now is we're going to look at, we're going to build a neural network, a fully connected neural network. We're going to use Pytorch, and we're just going to build a simple network like this. It has input layer, bunch of hidden layers, and an output layer in order to be able to predict the surface roughness value, right? So the input layer, this data set has 12 columns. So the input layer will have 12 nodes, and the output layer will have one node, which is just going to output the value of the surface roughness for us. So the input layer will have 12 nodes, the output layer will have one node, and then it's up to us how many nodes we want to have in between. And it's just going to be a fully connected neural network just for simplicity, so to keep it simple. So what I have here is I have a Colab research collaboratory. I will share this with you in the chat that you can go to. If you have a Google account, log in with your Google account, and then you can connect to this Jupyter notebook that allows you, it's a collection of text cells and code cells, and it allows you to run the code and see what happens. Another beautiful thing with it is that you can essentially play around with the code in order to see what happens if you change something. And it's actually the best way to learn to see how these systems work, these tools work if you want to build a neural network. So what I have here is I have my data set. So if I just click on it, I have my data set, the CSV. I have uploaded it in GitHub, so you can easily download it with pandas. If you run the code, when you run the code, the data set is read using the pandas package in Python, and you can see the data set here. We have our layer height, wall thickness, infill density, infill patterns, and you have this nice button. If you click it, it uses Google Colab. We produce a bunch of charts for you, literally just with a click of a button, which is really, really nice. So you can actually quickly visualize different bits in the data set to see if there are any kind of outliers, if your data set is balanced enough for your model to learn all the patterns. So this is normally the first step before you build models, is you want to look at different charts and visualize and perform exploratory data analysis on your data set in order to see if there are any kind of outliers in this data set that you need to take care of, or whether you need to clean this data set, right? So you can see the different relationships between the different columns. So we have a good distribution of wall thickness and okay distribution of infill density. The layer height distribution isn't as much, so we may want to collect more data on layer height. But you can see that the infill pattern and the material, there is enough categories of each of them. So the model will see a good amount of, they will see a balanced in number of observations of each category, right? So these are like different charts that allows you to visualize this data set, and it's only like 50 rows. So there isn't a lot of observations in this data set. So whatever model we build on it, it's not going to be as good, but you will know that essentially like this is just like a demo data set that allows you to play around with these technologies, right? So what we will do in the next code cell is we're going to drop any kind of null values that we have in a data set. So if you have any rows of data that have empty values in it, the drop NA will drop those null values, those rows that have any kind of empty values in it. We're also going to drop the, we're also going to create two separate data sets, X and Y. The X data set will not have the surface, the roughness column on it, whereas the Y data set will just have the Y roughness column. So X will become our features that goes into the model, and Y is the feature that is going to, it's the label that the model will try to learn on, right? So normally this is the process you want to do, is you want to separate the features and the target. So the target here is the surface roughness we're going to train a model on, and the X will be the features. And essentially, if I go up, you will see that in this data set we have columns that have text in them, like the info pattern and the material ABS. So what you want to do with these ones is you will want to perform a process called encoding categorical features. So scikit-learn is your tool for doing that. So scikit-learn allows you, it has in the processing package, has a label encoder that allows you to encode any of these columns, they're the ones that have text in them, into numbers. Like 0, like assign 0 to grid and honeycomb to 1, for instance, or create new columns with zeros and ones in them, and replace these columns that have text in them. They're categorical columns in them. You want to do this because the model that we're going to build, the neural network, can only accept numbers. It doesn't understand text. You can only pass array of numbers into it, not necessarily text. So you do this encoding to pass text into it. So your X will now have encoded variables, encoded categorical columns as number columns. Another thing that you will want to do is any column that have numbers in it, you see like 220, 60, you want to squish and standardize or scale these numbers between 0 and 1 so that the training process becomes faster, and just in case you don't explode any kind of when you're doing the multiplication, you don't explode that multiplication. So you also normally scale and standardize the features using a standard scaler in order to help with the training process. So you squish the numbers between 0 and 1, for instance. So you will have a scaled data set that is also all just numbers. And then at the end, what you need to do is you need to convert the X scaled, which is just a pandas data frame, into a tensor, so that then you can move it between a GPU and a CPU in this deep learning framework. So you use the Pytorch library to create a tensor, which is just like a NumPy array, but it's a data structure that can be passed between a CPU and a GPU. So you convert one for your features, and then you get one for your labels. And you also flatten the label using this .view function, so that it's just a list of numbers. There is no additional packaging going on. Then you use the scikit-learn's train test split to test this data set into a training data set and a testing data set. So you have 50 rows of data. You want to do perhaps a 20% of that data set becomes testing and 80% becomes training. So if you have 50 rows of data, for training, you give 35 rows for training by random. So you shuffle the data set and you grab by random 35 rows, and then the rest of it goes for testing. So this testing is set of rows that the model has not seen before at all. You just put that aside so that when you have a trained model, you can then test the model against it. Next, you need to create a data loader for the training data set and a data loader for a testing data set. In Pytorch library, you will want to use a data loader because you want to iterate over the data set and you want the data loader to return you a batch of rows, right? So in here we have a batch size, and every time that you iterate over the data set, you can shuffle and grab a batch of rows. So this data loader is essentially a mechanism for TensorFlow, for Pytorch to iterate over the dataset over and over again and grab a bunch of rows from that dataset, sample a bunch of rows from that dataset as a batch that you can iterate over and pass through the model. So instead of passing individual items to the model, individual rows, you pass a batch of rows so that you make the process of training much, much faster during this process. Right, so we did a bunch of data cleaning and data processing. We then did put stuff into a tensor and splitted the data set and then created our data loaders so that then we can go and start building our neural networks, right? So if I just go in here and I look at the X scaled for you. So if I just look at the X scaled array, you see that the X scaled is just basically our data set, but in a multi-dimensional array that has all of our data basically standardized in a standardized manner. So in this case, the data set has been squished between one standard deviation with an average of 0, with a mean of 0. That's what this scaling does in this case. So instead of squishing it between 0 and 1, the scaling has squished it between one standard deviation with a mean of 0 to make the training process smoother. So that's what we see in this case. Then before we create our training loop, what you want to do is you want to create a neural network. So if we go back to our visualization, we're creating a neural network that has how many nodes? 12 nodes on the left hand side, or 11 nodes on the left hand side for features, one node for the label that we're trying to predict, which is the surface roughness, which is a value, and then any number of one or two or three number of hidden nodes in between, and they're all fully connected. The way to do that in Pytorch is you specify a class that inherits the neural NN module. So that's what the inheritance does here. It carries over the features and the benefits from the NN module. And then in the init function of this class, you essentially trigger the init function of the neural network class itself, but then this is where you actually can create your neural network. So you create the first fully connected layer using the nn.linear. You pass it the input size, whatever the input size will be passed into this neural network, 64 output nodes. In the next layer, which is the fully connected layer, the second node, you create another linear layer. It has 64 input nodes, which is basically these two numbers need to match because you go from the left-hand side to the right-hand side. This will be 11 nodes, 64 nodes, then 64 nodes, 32 nodes output from this layer. And then in the next layer, the third layer, you have 32 nodes coming in and one node going out, which is your surface roughness, right? So if you visualize this, it would be 11 nodes on the left, 64 in this node, 32 at this node. We don't have hidden layer 3. We just have one output node going out. That's what it's going to look like in this case. You also will need to implement a forward function, which essentially allows you to pass the output of the first layer through a ReLU activation function, then pass the output from the first layer to the second layer, and then again pass the output of the second layer to the activation function, and then at the end pass the output of the second layer to the last layer to get the output. So this is basically what this forward function does. It passes the data through the network, one layer at a time. So using this approach, using this pattern, you can create any kind of neural networks that you want. Then you need to do something with this class. Once you have specified it in Python, you need to instantiate it, and you need to pass the number of input nodes that you want. Now, instead of hard coding 11 here, what we've done is we have used the xtrain array and accessed its shape value and grabbed the first item in it. So this will give you the size of that model, which is 11. So you can see in here, input features is 11, output features 64, input features 64, output features 32, input features 32, output features 1. And all of these layers have the bias element as well. So you will add biases as well, which is, if you remember, there was this p value. So all of those layers will be using this p value. So it can have more degrees of freedom to map the input to the output. So you have a initialized neural network. So essentially what we have at this stage now is this neural network that you see on the left hand side in this diagram. So we created a neural network that looks like this, is untrained. What we will need to do is we need to specify a bunch of configurations for the training process. So we specify a mean squared error loss metric for it as the criterion, and we specify an optimization algorithm called ADAM. So it's called adaptive moment optimizer. It's a training algorithm that tries to train the neural network. You pass it the model parameters with a learning rate of 0.001, very low rating rate, so that the algorithm doesn't overshoot during the training process. In the next step is where you implement the training loop. So what you do is you iterate over the number of iterations that you want across your dataset, number of epochs. So you create a training loop where you iterate over each epoch. You set the model into training mode so that the model weights gets adjusted. You instantiate the running loss to 0 so that you can then compute the running loss. You then iterate over your train data loader. And in each iteration, you get two values. You get the current X batch, so the current input batches, so the current input features, so a batch of entries, and your labels for that batch. You set the weight adjustments to 0, so you reset them if you haven't. You set them to 0 so you can start from scratch. You pass your current batch through your neural network to get the outputs for them. So these outputs will be basically outputs of predictions on the surface roughness for those inputs. So those would be 35 observations, for instance. You then pass those outputs with those labels. So you pass the predictions and the actuals for that batch to the loss function to calculate the loss. And the loss could say, for instance, 500. So it's a sum of all the loss across all the entire data set, mean squared error loss, basically. Then you perform a backward pass through the neural network. And what this loss.backward does is it calculates how much you need to adjust the knobs and dials. So if you go in here, that loss.backward will calculate whether you need to adjust each of these parameters towards the right or towards the left and how much. The optimizer step performs those operations. So the optimizer.step will actually perform the adjustment. So the loss.backward calculates the adjustment using differential equations and the chain rule. The optimizer.step performs those calculations by adjusting these knobs and dials on the neural network or adjusting the connections. Then what you do is you calculate, you sum the running loss by grabbing the by doing loss.item to add the current loss for the current batch into this metric that get adding up, right? So each epoch, you have multiple batches in it, so you need to iterate over each batch. So the batch size could be 2, and you have 50 entries or 35 rows. So you iterate over them to grab that batch, and you then need to calculate the epoch loss by dividing the running loss over the length of the train, or length of your data loader. So how many items you have in the data loader to calculate the average loss, and then you add the average loss to the overall training losses. So if you have 200 times, if you're iterating over your data set 100 times, and then you're iterating over the batches in that iteration, you want to have an average loss per iteration that you have done across your data set for every batch, right? And then in here, all you're doing is you're printing the, you're logging the results of the loss only at every 10 epochs. So you don't want to print results every epoch because your terminal is going to get clogged with lots of outputs. You only output the results every 10 iterations. So if you run this for 100 times, you will see that the loss for the first epoch is 40,000, and then it's going down gradually. Right, so 37,000, 35,000. So we iterated over our data set 100 times. So it's a very small data set. That's why it's so super fast to iterate over it. And by the 100th epoch, we got to a loss of 39,000, right? And we're only printing at every 10 epoch. That's what this line was doing here. And then once the iteration is done, we finish the printing. Next, what we want to do is we want to evaluate the results of the model. So we want to run the model against a test data set to see how much the model is doing, right? So this loss here is for the training data set. We want to do it against a testing data set. So this training data set is like homework questions. We want to test it on exam questions. And on the exam questions, normally the loss will be much higher than the training questions. So what we're doing here is we put the model into evaluation mode. We set the test loss to 0. And then we essentially, in the context manager, in a Torch no-grad context manager, we freeze all the weights and parameters so they don't get adjusted by mistake. Within the context of these frozen weights and parameters, which torch.nograd does, you iterate over the batches of the test loader of your test data set. So on your test loader, you iterate over the input features and the labels. You grab the input features and the labels of that batch. You pass it through the model. You calculate the loss for that batch, and then you compute the test loss, and then you calculate the average test loss. And the average test loss for that single epoch, single iteration over your test data set is 42,000. So your job now is to reduce down to 0. Another thing you can do is you can use the matplotlib package to visualize the train losses. So visualize the average loss metric across the batches, across the epochs. So if we visualize the epoch by the mean squared error loss, you will see that over the 100 epochs, the training loss is kind of like jumping up and down, and it's not actually reducing them to 0 as much, right? If you want to also see the data set against, if you want to see what the predictions are against the actuals, this code here puts the model into eval mode again, grabs the full set of features, makes the prediction across the entire data set using this line of code. It then drops all the null values and adjusts assigns the predictions to a new column called predicted roughness. And then it also calculates the squared error using this formula, which is the delta between the roughness and predicted roughness to the power of 2 to calculate the mean squared error. And it puts it back, and you can see in here that our squared error is quite significant because our roughness is 25, our predicted roughness is 0.03. Roughness is 68, predicted roughness is 0.01. So it's actually not doing a good job at all. It's really bad. It's not actually predicting things correctly at this rate, right? And if you go down here and we look at the overall squared error on the data set, it's about 40,000. And if you look at the visualization of our data set against the actuals, we will see that, yeah, it's not doing anything at all. It's not doing a good job at all. We haven't trained the model enough, perhaps. So the perfect predictions would be on the ideal fit on the line. So the predicted roughness and the actual roughness vectors need to actually match perfectly, correctly together. And if you look at the residual histograms, you can see that we have error rates across the different, we have error rates all over the place at this rate. So you can see the predicted roughness by the surface roughness across the entire data set is basically all over the place. We have error rates in all the different amounts, different bins in this histogram. So we have predictions that have small error rates, and we have predictions that have big error rates, and predictions that have medium error rates, mostly medium error rate predictions that have quite a lot. So one of the things you can do to improve this model is, if you go back up, you can perhaps try to train this model a bit further on the data set for it to improve better. That's one of the things you can do. And if you look at the model, you would be able to see if it's doing a good job. And you can see that just training the data set across the model isn't doing a good job at all. It's not actually training the data set. It's not actually increasing the training process as such across the data set. Right. So essentially, what ends up happening is that the model is not actually training and learning to an extent that you wanted it to learn. Right. So what you can do with this is you can go in and you can try to make the predictions further. You can try to run and rerun the model, and you can try to make play around with these parameters in order to set the training process in a way for the model to start learning the calculations better and better. So if I reset the model and I train it again, you can see that this time the model has learned to work across the data set at a much better rate. So you see in this case, what I did, I reset the model, I reset the number of epochs, and you can see in this case the model is training much better. If I look at the evaluation, you see that the test loss has decreased. And if I look at the training loss over the epochs, you can see in this case the model is dropping in the error rate as you increase the number of epochs. In the previous case, it wasn't training because I didn't reset the model. I had to reset the model towards zero, towards scratch, and retrain it again so that we get a better model at this case. So now, if you look at the evaluation of the model on the right-hand side, you will see that the predicted roughness is 24, roughness is 25, predicted roughness at 32, roughness is at 32, predicted roughness at 45, roughness is at 40. So it is actually doing quite a good job at this case. All by doing that specific, by just increasing the number of epochs. So you now see the overall mean squared error on the data set is much, much lower. And if we try to visualize it on the data set, you can see that it's actually doing a much better job. The actual roughness and the predicted roughness are now at matching the ideal fit. And if I look at the residuals, you see that the frequencies are lowering down, and most of the residuals, so most of the error rates, are near zero, which is good. You have a normal distribution around zero in terms of like your residuals, in terms of your error rates. But most importantly, you want to see most of these data points to lie on the actual red line. So if I go back up and I try to reset the model again, so I just run this line of code, and I set the, let's say I set the training number of epochs to, let's say 500 instead of 1000, and I train the model. I run the evaluation again and I run the visualization. Maybe 500 wasn't the right amount. Maybe I need to do it at a much lower amount. You can see it's still doing a good job on 500 epochs. Let me try to reduce the number of epochs to a lower value. So I reset the model again. Let me put this at 200 and see what 200 does to the model. So we train it at 200. Oh, this time it didn't go. It didn't actually manage to learn. Let me reset the model and try again. So if you noticed, every time I run the model, sometimes it doesn't learn. This is because of the random initialization that happens on the training process. So it sometimes doesn't train enough because you might end up on part of the loss function area that it doesn't give it enough time to reduce down. Ooh, this time we got down to a much lower value that we ran it. So only with 200 epochs this time we managed to get lower value. There you go. So one thing that you notice is every time you rerun the code, the neural network gets initialized at different points. And depending on where it gets initialized, the model learns easier and easier, or the model that doesn't learn in that case. So if you see that your model doesn't learn, perhaps one of the experiments you can do is rerun the code again by reinitializing the model at different area points and see if it learns in that case. So now if I go back down here and I run this code, you see that the model with lower number of epochs have a lot of more data points that are not lying down on the red line. So hopefully this gave you a bit of an idea of how you can build neural networks from scratch on a data set that the model hasn't seen before. So this is a data set that's not, MNIST digit numbers. It's an actual like real world data set where you can actually use it on 3D printed on 3D printed components. But yeah, essentially that's what I wanted to cover in today's workshop for you in that case. So we covered how neural networks work, we covered the underlying mechanisms with it, and we also looked at the demo of the neural networks with a 3D printed data set. We looked at different deep learning frameworks, what tensors are, how tensor calculations are done, how different deep learning frameworks train and load the model data sets. And also we looked at how to build a fully connected neural network and train it on our own data set at the end. So I hope you had I hope this was useful for you. You had a good idea around how these neural networks work. What we're going to do now is we have 5 minutes to 10 minutes remaining where I'm happy to answer any questions you might have in relation to that demo exercise, or if you have any questions in relation to the neural networks. So feel free to post in the chat and I will answer them now. Other than that, we basically wanted to give you another note that if you're more interested in generative AI as well, my book is going to be published in the next few months, where we're going to be going into and covering different topics in generative AI and how to build different generative AI services with Fast API, how to load AI models into this web framework, build type-safe AI services, implement concurrency so that you can serve it to different and multiple users at the same time, stream model outputs from it into your users, connect databases, build your authentication systems on top, how to secure it, optimize it, test your AI services, and deploy it at the end. So if you want to build a whole product as generative AI models from scratch, definitely do pick up the book to help you with any of those applications that you want to go further with. But yeah, if you have any questions, feel free to ask in the chat. I'm happy to answer them now. And I hope you had enjoyed today's webinar. So first question is from Padam, is asking if we decrease the learning rate further, if we decrease the learning rate further, the model might behave a bit better. That is true. So I think one of the reasons that the model was not behaving correctly in some of the training runs is if I go back to this view here, if you're trying to go down a valley, but you're taking really big steps, what ends up happening is with a large learning rate, you might end up overshooting the bottom of the valley. So the valley is a loss function. If you're trying to reduce the loss, if the learning rate is quite significant, what ends up happening is you will overshoot to the left and right of this valley, as you can see at the bottom right corner diagram. So one of the things we could try is to reduce the learning rate. It would reduce the speed at which the neural networks get trained. But on the other side, what ends up happening is you might end up having a more stable model. The other reason that the model wasn't training in some cases, so if you notice, the first time that I run it, the model wasn't training at all. And then the next time I run it, the model, I put 5,000 epochs, the model wasn't training at all. It was bouncing all over the place. The reason that it's doing that is because every time we initialize the model, the weights and biases get initialized at some random value. That means that on this loss function, you might end up in some area of this map where it's very hard to get to the bottom of it. So you might end up in like some weird mountain with lots of like edges around it, and you can't really go down this valley where you got spawned on this loss function. So just by reinitializing the model, you may randomly get placed in an area of the loss function map where it's much easier to go down using gradient descent, going down the mountain towards the lower areas of the loss function by adjusting the weights and parameters. So that's why we saw that the same code, when I ran it multiple times, in some of the times it was much easier to get a trained model compared to the rest. Another note as well is the model we have built might have includes elements of overfitting. It does includes elements of overfitting because there isn't enough entries in the data set for us to not overfit. So it will definitely pick up patterns in the data because we only have 50 rows. It will definitely pick up patterns in the data that shouldn't pick up. So it's memorizing some of the exam questions. We added some of the homework questions based on some of the entries that it has seen. Right, so that's this part about the neural network. Any other questions regarding some of the content that we covered today? All right. So if there is no further questions, thank you very much again for your time today joining us on today's webinar. Really exciting times for 2025. So we're going to be covering a lot of future workshop series. So you saw today that we covered deep learning. In the next workshop, we're going to go more into computer vision and different areas, and going to go cover those as well. I think before we say goodbye, I think I saw there's a couple of more questions coming in. One of the questions is asking if the book is on Kindle. The book is actually, if I just turn my webcam off, the book is on, will be on Kindle as well, yes. But at the moment you can pre-order the paperback version if you want. The early release chapters of the book are available on the O'Reilly platform. So if you just search O'Reilly Building Generative AI Services, you can get that. You can access all the chapters on the early release version, but they might have some errata just because we're still working through some of their comments on them, and there might be some changes. But if you can't wait until May, you can get the early release chapters. The full manuscript of the book is available on the O'Reilly platform when you subscribe to the O'Reilly. Otherwise, you can buy the book from the Amazon. MCR is asking, what do you mean by reinitializing the model and it will be at different points? That's a really good question. So let me go back to this picture here. So every time that you recreate the neural network using that code that we have, that class that we implemented in Python, these numbers that gets assigned to the weights on this neural network will be some number between 0 and 1, especially mostly between like some number between near 0, like 0.01, 0.02, minus 0.01, minus 0.02, and these numbers are random, but they're near 0. What researchers have found is that if you initialize the model, the neural network, with weights that are near 0, the chances of you getting a trained model in that training process is much higher compared to if you just put some bunch of other random values on this weights and biases. So because of this randomization, a random initialization process where you randomly put some weights on these connections, what ends up happening in terms of the loss function is that on this n-dimensional landscape, that is your error function, you are essentially initialized somewhere on this landscape. So you might get initialized at the bottom of the valley, you might get initialized at the top of the valley, you might get initialized somewhere where it's much harder to get to the bottom of the valleys, and it makes the gradient descent process much harder. that's what I mean by getting initialized at different points in the modeling process. Because of that process where you create a model and you have to put some random numbers on the weights and biases before you train it. So on the untrained model, depending on what random values get assigned to those connections, the loss function where you are on the loss function map will be different. So running the same model in different areas might put you in different areas. If your training loop isn't implemented correctly, you will never get to the bottom anyway. So it doesn't matter where you get initialized. But if your training process is correct, and you try it one or two times and you feel like you're not training, try it a few more times. And if it still doesn't training, maybe it's a problem with your training process. Otherwise, you just got unlucky. You may want to rerun the code again to make sure that this time you get initialized at the right place. So this is still an area of research. How can you create a model and get reinitialized at a better place in this loss function so that your loss rate reduces much smoother and much faster? All right. Any other questions? So yeah, apologies. I feel like we didn't have any questions, but I'm happy to answer any more questions that you might have. Yes, I'll happy to explain the book as well. So building generative AI services, essentially, if I just turn my webcam off as well, this is a book if you want to build applications with like chatbot applications, content summarizers, talk to your documents apps, building image generators, text to speech applications, text to audio, text to music, text to image, chatbots. If you want to talk to your documents, you upload a document to a chatbot and talk to it, like similar to ChatGPT. So if you're interested in building ChatGPT-like applications, this book will essentially teach you how to do it in Python. I use a web framework called FastAPI, which is one of the most popular web frameworks in Python. After FastAPI, you have Flask or Django. This book focuses on FastAPI and how you can use different features of FastAPI to build your backend. And essentially, it introduces you to the whole generative AI tools, as well as generative AI models. What are the different types of models we have? And also teaches you how can you create different services from different models. So some models will help you generate text. Other models will help you generate audio, video, images, 3D geometries. So third chapter, for instance, will teach you how to work with each of them. I'm also doing that workshop in April, 1st of April at Reactor, to build some of these tools together with you. So if you're interested, you can come to that workshop. I think there's only 35 spaces for that one. But if you're interested, yeah, you could come on that workshop and we will actually do a couple of these applications together. The rest of the book focuses on how can you serve these models to multiple users using concurrency. How can you make it real time so that you don't have to sit around and wait for the generation to happen? You can actually, just like ChatGPT, get the results coming at you in real time, word by word, as the data is being generated. So it works on real-time model streaming. The chapters 7 to 12, 7 to 10, and 12, all the way towards the end, focuses on how do you actually implement an authentication layer on top. So your users have to log in to use the app. You protect your endpoints from getting abused and misused. If you're building some kind of application with large language models, what are the different types of security considerations you need to have, like attack vectors? So there are concepts such as prompt injections, prompt hijacking, data poisoning. So these are the concepts we will talk about in the chapters on securing AI services. And then how can you make it faster? Optimizing AI services focuses on that. How can you use more compressed models through the quantization process? How can you use the batch processing APIs with some of these models? So if you're going to be working with OpenAI API, how can you use that to batch process your documents? For instance, how do you test services that have AI models in them? because the AI model is going to be probabilistic. It's not going to return the same results every time. So how can you write tests against the model that produces something different every time? That's what chapter 11 is going to go into: best practices with software engineering for testing, but also with AI services. And then last chapter, we're going to focus on Docker as well as other patterns for you to be able to like build these AI services on top. So how can you package your application once you've built it? Let's say you have a fast API app. It's just the main.py with a bunch of code in it. How can you use Docker to containerize it and then deploy it into like some cloud provider, or deploy it on your own computer, like host it on your own computer so others can come and use it, as long as your computer is a server. So how can you use deployments on virtual machines, on cloud functions, as well as containers? And it's going to mostly focus on containers because it's a really good deployment pattern to deploy your fast API service wherever you like. Most of the focus of the book will be on open source models. So if you're familiar with the Hugging Face website, it has a model repository of about 1 million models. Some of those models will be generative AI related, and we're going to be using a lot of open source models. It would be ideal that you have a GPU machine, but otherwise it still runs on CPU. It's just it might be very slow. But if you have a GPU system, it allows you to actually like experiment and see how some of these models work and interact, especially open source ones. So like an open source small language model, open source stable diffusion model that generates images or generates videos, animates videos. For instance, you upload an image and it animates it for you, just like those Harry Potter newspapers, like the newspaper images in the newspapers move and animate. Just like that, you can upload your image and get it to animate with these services. So it shows you all of those things. Like for instance, there is OpenAI Shapi, which is a model that allows you to generate 3D geometries. That one is also very interesting because it lets you the 3D geometry one lets you essentially create any shape, especially let's say you're building a game. Instead of having to create a donut in 3ds Max, you can use OpenAI Shapi to generate a donut. Even though it's going to be very low fidelity and like it has a lot of problems, you can still generate that mesh and then import that into 3ds Max and work from it instead of having to start from scratch. So it's really good in like the designing and build these kind of services that uses generative AI for the various different applications. In particular, a lot of companies are interested in chatbots, where you can connect the chatbot to your knowledge base. There is a process called retrieval augmented generation. That's the process where you connect your chatbot to a knowledge base, and then you can perform searches across your knowledge base. And then the chatbot will fetch the right documents, relevant bits of the documents for you, and you can talk to those bits. So if you ask a question, it goes and fetches the right stuff. It then talks to you about them and answers your question. So any kind of question answering apps, it also helps you build those. So it's really, really good for these kind of like services if you want to build that. So I will go into all of those details. It's about 400 pages. So it goes into all sorts of details with building generative AI apps. I mostly focus on building than explaining what's going under some of the models, but the whole chapter 3 will go from focus into how some of these models actually work. So you have a bit of an intuitive understanding of this work instead of going into the mathematical details. All right, no, thank you very much. MCR, thank you very much for coming to today's workshop. And yeah, if you, I will be posting the workshop for April. But before April, we might have a couple of other workshops. So we might have another workshop on convolutional neural networks or text classification with transformers, as well as a reinforcement learning workshop. So have a look out for other webinars coming. We may also post a couple of talks as well. But the generative AI workshop will be in April, 1st of April, if you're interested. So it will be a classroom style with 35 people max. It will be free. And we're going to be working with Microsoft Azure AI, Azure OpenAI and Azure AI Foundry to build this generative AI service together. And the other workshops we have planned for 2025 include machine learning, regression, classification, clustering, time series, cloud computing, and data streaming. So there's a lot of good technical stuff in here. In the machine learning workshop, we're going to go back to the roots again, to the fundamentals, and we're going to talk about the fundamentals of machine learning. So if some of the concepts of today felt a bit out of depth, in that definitely come to the machine learning workshop. We're going to focus on the beginnings, on the fundamentals, and work our way up and explain what are the different concepts, like what is supervised learning, unsupervised learning, what is reinforcement learning. So we're going to go cover all of those bits in more detail if some of those bits you didn't connect with in today's workshop, today's webinar. All right. All right. Well, thank you very much, everyone. I hope you enjoyed today's webinar. And if there's any more questions, hope you have a good rest of the day. And I'll see you in the next webinar series we're going to be posted very soon on our Meetup and Eventbrite channels. If you haven't subscribed, feel free to subscribe to the channel as well, so you get new notifications if there's any more webinars or any more live streams going in the future.